Okay. Section 6.4 will be on sampling distributions. Now, we've talked about samples before, and some of this stuff you may have already seen in previous sections. But this is gonna be really important, especially as we go to the central limit theorem in section 6.5. So I want to briefly go over some and review some things that we learned when it comes to samples here. So when we talk about population versus sample, for a population, the data is from every individual of interest. And when you have data from every individual of interest in your study, this data is fixed and complete. So I think a while back we used the Mount Everest example, right? If you have getting a population study on people who have climbed Mount Everest, we have data from all of the climbers, and there's not that many. And sample data the data is only from some of the individuals of interest, and depending on the sample, the data may vary. And for obvious reasons, it's not complete. And if we're using the Mount Everest example, let's say we have data from only some of the divers. Let's say we only have data from divers under the age of 40, or climbers who are who maybe are above or below a certain height or build. And of course, we talked about a statistic versus a parameter. A statistic is a numerical descriptive measure of a sample, while the parameter does the same thing, but for a population. Now, again, for a population, a specified parameter is fixed. But again, because the data varies from sample to sample in sample data, a statistic might vary depending on which sample you choose. And of course, we use, you've seen this before, we use X bar for the mean of a statistic, mu for the variable for the mean of a parameter. With variance and standard deviation, we use a lowercase s for statistic and the Greek letter sigma for parameter. Okay? And we've all seen this before. So if I wanted to create a study on the daily amount of soda the average teenager drinks, what type of data would be more appropriate to use? Population data or sample data? We talked about this in chapter 1 when we talked about population versus sample. What's our subject? The average American teenager, of which there are billions upon billions. Well, let's say millions upon millions, since we're talking about America. A sample data would be more feasible and probably would be more appropriate, because to get every single American teenager would take time, money, and manpower. Okay, sometimes we don't have access to all of that. So in this case, if that's the case, then we use measurements from a sample, and this is where we use a statistic to make an inference about a corresponding population parameter. And here are the 3 different types of inferences. So there's estimation, there's testing, and there's regression. In an estimation, this is where we estimate the value of a parameter. With testing, we formulate a decision about the value of that parameter. And then when we get to regression, we make predictions or forecasts about the value of a statistical variable. Okay, so, and you could probably think of this as a terms of progression, right? You start with an estimation. You could start with an estimation where you think your parameter is going to have this type of value. In the actual testing phase, we make a decision about what the value of that parameter actually is, and then based off of that value, then we can make predictions or forecasts about the value of that variable. So, to evaluate reliability of our inferences, we need to know the probability distribution for the statistic that we're using. This is called a sampling distribution. A sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples from the same size and from the same population. So that's really important. The samples have to be of the same size and of the same population. Okay, so here's an example. Pinedale, Wisconsin is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches may be returned to the pond. Only children 12 years or under may fish, and a limit of 5 fish may be kept per day. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. The pond contains only rainbow trout and has been well stocked for many years. Each child has no difficulty catching his or her limit of 5 trout. As a project for her biometrics class, Susan kept a record of the lengths to the nearest inch of all trout caught last summer. Hundreds of children visited the pond and caught their limit of 5 trout, so Susan has a lot of data. To make that table, she selected 100 children at random and listed the lengths of each of the 5 trout caught by a child in the sample. So here is the sample, right? So she had hundreds and hundreds of data points, hundreds upon hundreds of data points, 5 for each child. So she took a random sample of 100 children and compiled the length to the nearest inch. And then for each child, she came up with a sample mean here. And then here is the frequency table for this group. I mean, you got your classes, your class limits, your frequency, and your relative frequency. Look how perfect, almost perfectly bell-shaped this distribution is, right? Even with a small sample space and a small number of fish, the graph, you could see it was roughly bell-shaped and symmetrical. So if you want to fix that, if you want to make it more even and more bell-shaped, you can fix that by both increasing the number of children and increasing the number of fish caught per child. As this continues to happen, then this graph will eventually become perfectly bell-shaped, and this will lead us to the central limit theorem in the next section.